Okay, so with that said, if my memory serves me well, I think we finished the temperature-mediated control methods. Did we? Yeah, I think so. So we're going to briefly talk about some other physical methods of the control of microbial growth. The first one will be the radiation. It's basically the second largest, if I can say, method. There are two types of radiation-mediated control methods: ionizing and non-ionizing radiation. Generally speaking, the ionizing radiation methods can be performed by using X-rays or gamma rays. You can see that these wavelengths, the X-ray, the gamma ray, are in the short wave high energy part of the electromagnetic spectrum. This radiation is called ionizing because it leads to the formation of, obviously, ions. These ions, when they are formed in the cell, lead to the formation of strand breaks, either single or double strand breaks. We talked about this mechanism of mutagenesis before. Essentially what happens is the amount of mutations that accumulate in the DNA of bacterial or viral cell, or a bacterial cell or viral particle, go way over the capacity of the cell to restore the integrity of DNA or to successfully replicate. The advantage of ionizing radiation, of course, is that it is sporicidal. Can be used for sterilization. Okay, so it is used for food sterilization. In Europe, it is very widely used. In the United States, not so much. But there are certain foods that are exposed to gamma irradiation before they hit the store shelves. Those of you who like mangoes should know that mangoes are exposed to gamma ray irradiation in order to preserve them from fruit flies. Turns out not only you, but fruit fly larvae love mango very much, and fruit flies deposit eggs into the mango skin. These eggs eventually hatch in the larva, and the last thing that any store wants is the customer that poops out those fruit fly larvae, which is absolutely benign but can freak people out. So essentially, when mangoes are exposed to the gamma rays, eggs are killed, larvae killed, and nothing emerges from them. It's important to notice that any exposure to either X-rays or gamma rays does not induce any residual radioactivity in the food. Does that make sense? In some rare clinical instances, for instance, if you have a patient who is extremely immunocompromised, whether due to the treatment or genetically, you may want to sterilize the patient's food to prevent any possible oral transmission of infection. In this case, of course, the first choice of the sterilization protocol would be the X-ray. The gamma ray. Does that make sense? And hospitals have gamma ray cannons routinely, so it's not something out of the reach. Another application of gamma ray sterilization is medical and laboratory plastic. It's actually quite common. It's convenient because temperature-sensitive items can be sterilized, and sterilization can be performed in sort of a conveyor fashion. You can basically run a conveyor belt through the gamma ray chamber where plastic goods will be exposed to the radiation. Does that make sense? So it's sterilizing great technique. Now, obviously the downside of gamma rays is that they are extremely aggressive and have to be used with a lot of precaution measures. Now, UV light, although it's disinfecting rather than sterilizing, is widely used for disinfection of medical surfaces, disinfection of surfaces in the food prep facilities, and for water disinfection. So water can be exposed to UV light in the flow manner. You know what I'm talking about? So basically you have water flowing under the UV light. UV light has enough penetrating capacity to destroy vegetative bacteria. These systems essentially can replace the chlorination systems or saline systems to control for bacteria in like public pools. It's more expensive, okay, but it, allows you to swim in the normal fresh water without any added chemicals. You all know, you also use the light in the food prep facilities, in the medical offices. This is used to essentially disinfect surfaces or the air. Safer, not 100% safe for humans, so we shouldn't be exposed to it directly. The mechanism of the UV light, as we mentioned, is the formation of diamond diamonds. Now, another important thing is that, these three types of rays have different penetrating capacity, meaning that gamma rays have excellent penetrating capacity. The barrier that will contain them would be something like 1 meter of concrete or 5 centimeters of lead. X-rays, less penetrating capacity but still considerable. And finally, UV light can be contained by a layer of plastic, or glass completely contains UV light. Does that make sense? Now, the third method that I want to mention is filtration methods. As you can imagine, filtration cannot be used for disinfection or sterilization of solids, because you can't really filter solids. But it is very convenient for disinfecting or sterilizing large volumes of fluids, and especially gases. You can imagine, I believe, putting a fluid that you need to sterilize, say a solution, into the flask, sticking the flask into the autoclave and running the cycle, sterilizing the solution. It's easy, it's feasible, But doing the same with air seems absolutely counterintuitive. How can you trap air for 40 minutes in an autoclave and autoclave the air? This is why filtration is the method of choice for sterilizing large volumes of air. Filters that are used for air disinfection and sterilization are often referred to as HEPA filters, high efficiency particulate air filters. They're used in various settings, from operating rooms, especially for victims with severe burns. And those victims lack of integumentary system exposes the underlying tissues to a lot of pathogens. We watched a movie about BSL facility. Okay, that's another expensive, yes, a lot of energy cost, but highly efficient. This graph shows you the brief representation of the filtration systems that are at the human disposal. And it's quite marvelous, really. So we have filters that can contain things from bacteria, rather small, but to actually chemicals like pigments are large organic molecules, to smaller organic molecules like sugars, to systems that allow to remove ions from water, which essentially in the end will give you water in its most pure form. It's going to be H2O and nothing else. Okay? In the lab and in the industrial microbiological applications, those systems are rarely used for treatment of, chemical compounds, or solutions, because they will remove the content of the solution. Filters that are regularly used in industrial applications are usually about 0.1 micrometer. They will remove pyrogens, lipopolysaccharides of gram-negative bacteria. So these are two examples of the laboratory filters. This one, as you can see, is attached to the tip of the syringe. It's pretty convenient, especially when you need to make a small injection to an animal, for instance. Or you just need to filter a really small amount of fluid for, say, experimental purposes. On the left, it's the typical filtration unit here that is attached on top of the flask. Thanks to standardization, those filtration units and necks of the flasks, basically all flasks that are produced in the United States, they match each other. So you can buy a filter from Wheaton and you can buy a flask from Corning, two completely different companies, and they would match. And then you attach it to the pump, and the pump will suck the fluid through the filter, filtering it out. Important advantage of filtration, of membrane filtration, is that you can sterilize heat-sensitive solutions. Imagine for a second that you need to sterilize, say, isotonic solution, sodium chloride. You can put it in the flask, you can stick it in an autoclave, you can run the cycle, and it will be sterile. Does that make sense? And sodium chloride is not going to go anywhere. Now, if you need to do the same with a solution of some kind of a drug, say antibiotic, that is heat sensitive, you cannot autoclave it because antibiotic will degrade at the higher temperature. In this case, filtration is an option. Does that make sense? Any questions? So as I mentioned, for this methods, there are a few things that I mentioned, like I specifically discussed pasteurization, in which microorganisms can be destroyed by pasteurization and what's common in between them. But I want you to focus on whether the methods are sterilizing or disinfecting and what you're going to use them for. Am I clear? Things like, if you need to sterilize heat-sensitive plastic, you shouldn't autoclave it, right? If you want to sterilize surgical instruments, autoclave is just fine. Am I clear? So this brings us to the discussion of various chemical methods used in the microbial control. The number of chemicals that we use in industrial, healthcare, or house applications is staggering. There are currently more than 1,000 different chemicals routinely used for microbial control. Some of them are solid, some of them are liquid. We even use gases. The overwhelming majority of them, they're liquid, they're water-based. But some are tinctures, meaning that they contain alcohol. What do you want your chemical to be? If you think about it, well, probably first and foremost, you want it to be effective. Act rapidly, so you don't have to leave it on the surface for hours. Preferably, this chemical should work well to low concentrations, in case, you need to dilute it. It should be, especially in the healthcare settings, it should be very resistant to inactivation by organics. What do we mean by that? So this statement, resistant to organic inactivation. If you apply chlorine or chlorine bleach to, say, blood, chlorine bleach will oxidize blood components just as well as it oxidizes bacteria, meaning that some of that bleach will be used for blood oxidation. Iron oxidation, oxidation of bar, for instance, any organic that contains in the blood. Does that make sense? So, ideally, your chemicals should be resistant to that process. You add in testing chemicals, and I read the National Institute of Standards and Technology, I think it's called NIST. They write standards for different procedures. So in NIST standard on antibacterial chemicals, one of the controls that has to be done is the control for inactivation. They use organic compounds to mix with the chemical and see if chemical works effectively. Does that make sense? So basically what it means, if I spray my bleach on soiled floor, blood soiled, feces soiled, bleach still has to work. Good? It should be non-toxic. Yeah, good luck with that. High surface penetration. If you take a look at the tables that you're sitting at, that's plastic. One of the main reasons it's plastic is because it's non-porous. Nothing can be absorbed in it. Everything that you spill on that plastic, bless you, stays there and you can efficiently inactivate it. Does that make sense? Nobody does like wooden tables anymore because it's just not safe, because something gets absorbed there, you have to burn the table. Non-corrosive, non-staining, deodorizing. Now that's really important. So think about this. Smell. For your household, you have to come up with something that smells at least acceptable, right? Non-staining, betadine that you use to disinfect a patient's skin. It's a great disinfectant, but you're not going to spray it on your kitchen counter. I mean, you can once, and then you will have to replace the counter because it will all be stained. And corrosive properties are really important. When I worked in research lab, we worked with viruses. We had to spray the cards, like office cards, with disinfectant. And this disinfectant was extremely corrosive. So eventually we had to replace all metal cards with plastic ones, because metal cards were just falling apart. Okay, so that's a problem. It should be affordable. It should be stable. Now, stability is a tricky thing. Let's say in the household, how often do you replenish the bottle? Maybe once every 2 weeks, So I mean, if it stays stable for 2 weeks, it's fine. Okay? If you have to store large amounts of the solution, it should be stable for the time of storage. That same corrosive chemical that I mentioned, called Clydex, according to the manufacturer's instructions, it has to be made fresh every 2 weeks. And you may think, who cares? Well, believe me, we had safety officer. She walked around every damn week and checked the date on the bottles with Clydex. And you could get scolded for having your Clydex expired. Every week she would check bottles in the entire buildings. Okay, so that was real, because it loses the activity pretty fast. Now, if you would look at the list, the requirements, it's not possible. It's some kind of a magic bullet. And you will see that, the more efficient the chemical is, the more toxic it is, or more inconvenient it is to work with. And safer chemicals are, generally not as effective. Now, that's your wish. What do you have to consider when you choose an actual agent? Well, nature of microorganisms. Look at the table at the bottom. So what this table shows you, on the left, there are a lot of different chemicals. Here, this row represents different microorganisms, various times of exposure, and the numbers demonstrate the decimal logarithms of reduction. It sounds terribly complicated, but it's not. So say if, let me find something more, if this is 1.1 decimal logarithm of reduction, it means the number of microbes was reduced about 10 times. Does that make sense? Here, the number of microbes was reduced 10,000 times, 10 to the power of 4. The bigger the number, the better. Does that make sense? So you can see that, different chemicals have different efficiency. Among those that were tested here, there were kind of, I would say, two sort of moderate failures. Lysol, disinfectant, and Mr. Clean, and I want to focus. These are household stuff. Ethanol was efficient, which kind of both doesn't correlate and correlates with what we discussed in the antimicrobial agents lab, because here they measured the number of microorganisms immediately after the application of the chemical. They didn't wait for 2 days as we did. Does that make sense? And vinegar and baking soda, leave them for cooking. Okay? Just leave them for cooking. Now, what is kind of interesting, not only different chemicals have different efficiency, but there is difference between microorganisms. For instance, say, it's most obvious with vinegar and baking soda. Say, acidic treatment is not super efficient on Staph aureus or E. coli, but works pretty well against Salmonella and Pseudomonas. Now, if that would be up to me, my household, I would actually be more concerned about Staph aureus or E. coli than about Salmonella or Pseudomonas. That specific strain of E. coli, by the way, 0157H7, is the one that makes news basically every year. There's an outbreak of E. coli. About a year ago, there was a romaine lettuce. So that's the one. Okay, it's pretty nasty in terms of the disease that it causes. Now, what's also interesting is that if you would look at the table 3 in that corner, that's the data, similar data, for poliovirus. Now, we will talk why poliovirus a bit later, a couple of minutes, but look at this. So, for instance, ethyl alcohol that seems to work marvelously against all bacteria has practically no effect against poliovirus. Okay? Lysol is sort of better. Okay, here. But in general, you can see that poliovirus is much more resistant than any of 4 microorganisms shown in the table 1. Now, why poliovirus? Poliovirus here serves as a model. Poliovirus is non-enveloped virus that is transmitted by fecal-oral route. So it kind of exemplifies infections, viral infections that can be transmitted with food or water. Things like norovirus infections, enterovirus infections, common cold actually, although it's not fecal oral, but still pretty resistant. So it shows you, for instance, that while you can wash your hands or use hand sanitizer and get rid of bacteria in your skin, those same treatments, the hand sanitizer, for instance, will not be efficient against poliovirus. You see what I'm saying? So if you want to get rid of the viruses, mechanical removal is your choice, because I doubt that you're going to bath your hands in the Clorox, okay, like chlorine bleach. So you have to consider which microorganism you're trying to extinguish. You have to consider the task, okay, what you're treating. If you soak surgical instruments made of, non-corrosive steel, it's one story. If you wash floors, totally different story. You won't be able to soak the floors for hours, right? So that's the thing. How badly the surface is contaminated. Whether there is any other soilage, like feces or blood, that will make a difference. Actually, even the material will make a difference. Whether you cleaning solid surface or porous surface will make a lot of difference. But in general, microorganisms demonstrate the same hierarchy of resistance as we discussed before, and the spores being the most resistant. Then you've got various protected forms of microorganisms such as cysts, sexual spores of fungi. And then you have vegetative bacterial cells, protozoan trophozoites, asexual fungal spores, and fungi themselves. Does that make sense? Those three groups that we discussed in the very beginning of the topic still stand. And this brings us to the conversation about the first group of antimicrobial control chemicals, halogens. Halogens, now I'm going to give way to the inner chemist, our 17th group in the periodic table. They are among the most oxidative chemicals, most oxidative, I should call them chemicals, in the entire periodic table. There are 4 of them. Well, technically there are 5, but we're not talking about astatine because it's radioactive, super expensive, artificially produced. So 4 that I want to mention are fluorine, chlorine, bromine, and iodine. Nobody uses fluorine since it's extremely reactive. If you mix fluorine with hydrogen, for instance, it explodes, just explodes. Just you mix them and they just explode. So fluorine is not really usable for anything like this. Now bromine is not usable either, although interestingly enough bromine is a liquid at the room temperature. But it's very heavy and aggressive liquid that produces highly toxic vapors. Okay? If you ever worked in a chemical lab with bromine, I would say I have an experience working with bromine and working with chlorine. Chlorine's easier because it's a gas, and if it escapes, it kind of dissipates in the air pretty quickly. Bromine's vapors are very heavy, and they stay above the liquid. And if they will escape, they will spread very closely to the surface. You basically can see these brown vapors spreading from the open container. So it's really not an option. So in the end, we use 2 chemicals. We use chlorine and we use iodine. Now chlorine, as you may know, is highly toxic gas. Its toxicity was successfully proven in 1915 by Germans. Ypres, in France. So we don't use pure chlorine. Nobody's going to go into the Home Depot and buy a tank of chlorine. What we do instead, we mix chlorine with water. And this solution of chlorine in water produces acid, hypochlorite anion, and some chloride anions. Now, when you go and buy chlorine bleach, you essentially buy acidified solution of hypochlorite. Next time you buy mold mildew remover, or that Clorox cleaner plus bleach, look at the ingredients. It's going to say something like hypochlorite or sodium hypochlorite or hypochloric acid. When you start spraying it, say in your bathroom on the walls to remove mildew, you feel the smell of chlorine. And this is why you need to use it in a well-ventilated room. Chlorine is pretty heavy, so it'll stay at the place of application, okay? And in my experience, I spray my bathtub, and I have to take few steps away from it, take few breaths, then come back, hold my breath, rub it, and then go away. Because chlorine just, it's a poisonous gas, so you've got to be careful with that. It's extremely efficient, okay? In high concentrations, with a long exposure, it's sporicidal. However, I want to make it clear, we do not use bleach to kill spores, just because we don't have that much time. Okay? Now, this is a really cool table that I managed to find. So it shows you the contact time for 99% inactivation of the coliform bacteria. So look at this. E. coli. Sounds familiar? Enterobacter glomerans. It's been renamed. Now it's Pantuia glomerans. Enterobacter cloacae. Klebsiella oxytoca, Klebsiella pneumonia, Salmonella. Salmonella sounds familiar. Yersinia enterocolitis. Shigella. I don't know if you've heard about Shigella, but shigellosis is a terrible, terrible dysenteric disease. So all those microorganisms, if you think they are exotic, they aren't, can be fairly easily acquired from poultry, eggs, milk. Milk is unpasteurized. Okay, so they are zoonotic, can be acquired from dogs, cats. Bless you. So essentially, look at this. If you have the concentration of chlorine in 1 milligram per liter, which is really low, Shigella will be killed in 30 seconds. 99% of Shigella cells. Now, basically, what it tells you that you're really concerned about the cleanliness of a surface. Spray chlorine bleach and leave it there for 15 minutes. Virtually everything will be gone. Does that make sense? Now, to sterilize, to treat, to disinfect water, we use chloramine. The chlorinated pools, like public pools, they add actually chloramine. Chloramine produces ammonia, which also has quite potent antimicrobial properties, and hypochlorite anion, which essentially kills microbes. Does that make sense? So generally speaking, chlorine is disinfecting, works by oxidation. In large concentrations, long exposure can be sterilizing. Now, another halogen that we use in the practice is iodine. Iodine itself, has anyone ever seen an actual, not the betadine, but actual iodine in chemistry? Gen Chem lab. How does it look? Like iodine. What is it? If you heat it, it will become vapor. but at the room temperature it's crystals.
Yeah,
Okay.
like those, it kind of gives like a pinkish tint in the glass.
Yep. It's brown crystals. If you try to dissolve them in water, they won't. But they will give that pink to maroon tint to water. In order to dissolve them, in olden times, chemists used the tincture, so some water, some alcohol, and they also used potassium iodide, which increases iodine solubility. Now we use a polymer called polyvinyl pyrrolidone. You don't need to memorize any of the formulas, of course. Basically, the idea is that you have the mixture of alcohol and water with added polyvinyl pyrrolidone, and it efficiently binds iodine, and then you can use iodine for skin application. One of the major reasons, it's liquid, so it stays on the surface. It's not going to evaporate. It's not going to go away like chlorine, and it's much less aggressive. So it's really good antiseptic agent. Does that make sense? Now, alcohols. We use two. We use ethanol and isopropanol. Many years ago, in some cases, methanol was used. Do you know why methanol is not used in any human-related applications anymore? What do people do with alcohol? Drink it. Okay? Methanol is extremely toxic. 50 milliliters of methanol can kill you. Ethanol is toxic as well, but, much higher concentrations. And isopropanol, it has some toxicity, but if somebody will try to drink isopropanol or something isopropyl alcohol based, like rubbing alcohol, it's going to be metabolized to acetone, which is bad, but not yet lethal. You have to drink a lot, basically. The best, actually, prevention in the lab where I worked, we had, for research purposes, we had to have ethanol, 96% ethanol, with a label on it, which was saying buffer C. So only we knew that it was actually ethanol. Because lab's open, we're not there all the time, we don't really close it. Anyone could walk in the building. If somebody walks in the lab, just, walking around and sees a bottle of chemically pure ethanol, it's basically better than food grade. There you go. You can make your own vodka or whatever you want to make. So mechanism of alcohol action. Membrane disruption and protein denaturation. Mainly. It also sucks out the water, so desiccation, but mainly membrane disruption and protein denaturation. Now, it's really effective against bacteria, but not against spores. It's not sporicidal. And another important feature, it's much less efficient against non-enveloped than against enveloped viruses. So this graph and this table, we're going to chat about them a little. So first let's focus on this graph here. So you see the residual amount of 3 different viruses after being exposed to 70% ethanol for 30 seconds and 5 minutes. Okay? So you see that enterovirus 71 and rhinovirus, 2 closely related viruses, are basically minimally affected by exposure to 70% ethanol. Zika virus, on the other hand, is practically gone after being exposed to ethanol. Now, do you really have to be concerned about Zika virus on the surface in the healthcare facilities in the United States? The answer is no. Rhinovirus is your common cold. Enterovirus 71 is allegedly a possible cause of acute flaccid myelitis. Okay, so have you heard about the outbreak of a virus called EDV68? No, oh, good for you. It's actually going on in the United States. Numbers are relatively low. We're talking about hundreds of cases, but mostly kids, when they get exposed to this virus, which is likely fecally orally transmitted, they develop something that looks like polio. Majority of them recover. We know that it's not polio. It's a different virus and the rates are much lower. But majority of them recover, but some of them experience permanent neurological damage. Okay, and EDV71 may be causing the same kind of disease. And this table takes it one step further. So I highlighted the ethanol in this, inactivation story, and the activity of ethanol against adenovirus, enterovirus 68 and 71, influenza, rhinovirus, and Zika virus. So these numbers show you the logarithm of reduction. The bigger the number, the better. The bigger the number, the more efficient inactivation is. Does that make sense? So if you would look at enterovirus, 68, 71, and rhino, they are not really significantly reduced. Okay? The reduction is basically in the margin of error. Does that make sense? On the other hand, influenza or Zika are inactivated really well. And not coincident, and by the way, adenovirus is not terribly well inactivated. Okay, so let's look at the pattern. Adenovirus to entero and rhinovirus, they aren't inactivated well. Zika and influenza are. What's the difference between these 6 viruses? The ones that I'm going to circle blue are non-enveloped. They are not really sensitive to alcohol. The ones that I'm going to circle green are enveloped viruses, and they are sensitive to alcohol-based inactivation. What does that mean for you? Be conscious. If you're in the hospital, alcohol-based hand sanitizers, really good against influenza. That's what you have to be concerned now. It's still season, right? So use them. However, remember that common cold or a vast majority of fecally orally transmitted viruses, they will not be greatly affected by the alcohol-based rub. Use hand wash. Ideally, use both. If you can't use hand wash and you pass by the alcohol-based hand sanitizer, take a couple of pumps. It's not going to hurt, but may prevent transmission of influenza. Does that make sense? Any questions so far? Yes?
So polio will be the exception to the rule for them because it's non-enveloped?
Polio is non-enveloped. Polio will be... Hold on. Polio is right here. You see, alcohol is not really working on polio. These numbers, the bigger they are, the better. For polio, they're really low. Polio is non-enveloped. So polio, let's expand it. Polio, entero, rhino. These 4 viruses are very closely related. So they aren't really inactivated well. Does that make sense?
Yes.
So, a couple more chemicals. Peroxides. First, you all familiar? 3% hydrogen peroxide. Peroxides, as you can get from the name, oxidize. produce reactive oxygen species which kill cells. 3% hydrogen peroxide that you have at home is a great disinfectant. Okay? Does that make sense? Now, what if you want to make it a sterilizing agent? Two options. Option number 2, you can augment the effects of peroxide by making it an acid. This compound, called peracetic acid, contains the acidic hydrogen and peroxide group. Peracetic acid is the main acting component of the antimicrobial chemical called Surfactants. It's produced by a company which research and development headquarters is located about 20 minutes east from here. Stairs. Bless you. It's a great chemical. The only downside, it's super efficient. Very efficient. It kills everything, including bacterial endospores. The only problem, it's also very toxic, highly irritating, and you're supposed to work with it wearing an isolating respirator. It's so bad. I personally know at least 2 people who worked with it without respirator. Worked with it after 2 hours. You cry and your lungs are burning. I mean, you're not gonna die, but you feel like crap. Okay.
In one room, they had a break in a fire, and we had to.
In stairs?
We weren't allowed to go in there. We had to have our fire gear on, plus our respirators and everything else.
It's possible that it was the one that handled the spore cleanse or hydrogen peroxide. I don't even know if anyone would go there, would just say burn it completely. Because we're going to talk about another stuff that they make. It's called hydrogen peroxide vaporizer. I don't have a picture here, but that's a great machine. It's basically a box, size of one of these tables on the wheels. You fill it with hydrogen peroxide. I believe the concentration is higher than 3%. You roll it in the room. You seal everything that you want to remain intact. You press the button, you walk out, lock the door. And this vaporizer fills the room with hydrogen peroxide vapors. They penetrate into every nook and crevice. Okay? And they stay there. But if you can shut down HVAC in the room, that's even better. Because they will stay in the room. They will kill everything. And then you can simply suck it out. Okay? They use higher concentration hydrogen peroxide. I don't know. Spore cleanse, if you spill it on you, it's going to be bad. It's not terrible. Well, it's diluted. If it probably was some kind of a storage of peracetic acid, like the actual pure chemical. This is probably why you had to wear all that stuff. Yeah, but it's pretty bad.
They make a bomb for the back of our squad. It's similar to that. It's a smaller version. It's a bomb. They put it in the back of the squad, seal it all up, put it off, come back in, suck all the stuff out of it and everything in the squad, sterilized.
That's probably hydrogen peroxide, yeah. Yeah.
It's just a smaller version.
Mm-hmm.
So like a little canister.
Yeah, but in this case, you don't care about the canister.
Right.
Yeah. This machine, it's haulable. Like you can take it into the hallway, get into another room, run it there, run it here, run it there. So it's really useful for like surgical suite sterilization. Okay. Actually, you can see those vaporizers. Devices that sterilize endoscopes and stethoscopes usually use vaporized hydrogen peroxide. You stick it in, close the lid, turn the button on. It's all sterile. That make sense? Now, surfactants. Surfactant stands for surface active compounds. They essentially disrupt membranes. There are 2 types. The ones that we have in this room well, we actually have both types, but the ones that are most common are anionic. The soap, dish soap, that antibacterial soap over there, it's all the same. Okay. Why they are called anionic? You see this long tail? See it? And there is negatively charged anion, carboxyl group at the end. So the idea of anionic compound, anionic surfactant, is to incorporate its long tail into the bacterial membrane or any cellular membrane and disrupt it. Does that make sense? Now here's the problem. The charge of the bacterial membrane, or any membrane for that matter, surface charge is negative. Negative charge on the membrane and negative charge on the molecule of surfactant, they will repel each other. Does that make sense? So, in honesty, anionic surfactants like soap work best as, chemicals for sanitization, mechanically removing germs and soil from surfaces or from patient's skin. They aren't really killing microbes. Does that make sense? Now, the ones that kind of do kill microbes are cationic surfactants, quaternary ammonia. Next time you take a shower or wash your hair, read the ingredients on the bottle of the shampoo or shower gel. Among those, you're very likely to find words like cetylpyridinium or benzalkonium. Okay? So these compounds also have a really, really long chain, okay? Just like anionic compounds do. But instead of anion at the end of the chain, they have quaternary ammonia cation, positively charged nitrogen atom. Positively charged nitrogen will efficiently attract or be attracted to negatively charged membrane surface, will be incorporated into the surface, into the membrane, will disrupt the membrane, cells will die. Quaternary ammonia can be pretty efficient. You tested their efficiency several weeks ago. Microquat is the quaternary ammonia compound. In fact, the vast majority of household cleaning chemicals contain quaternary ammonia compounds. Okay. Now, sometimes they are even mixed with something like, chlorhexidine or iodine. So you can mix quaternary ammonia and iodine, making it even more efficient in, say, cleaning patient skin. Now, which brings us to a really interesting group of chemicals, phenols and bisbiguanidins, which is a tongue breaker, I know. A phenol. The molecule of phenol shown here, it was introduced into the clinical practice by a gentleman named Joseph Lister. He used a water solution of phenol called carbolic acid to disinfect patient skin and patient wounds. It's toxic, it's chemical irritant, but at the time that was the best option. Then eventually safer derivatives of phenol, such as O-phenylphenol, were introduced into practice. Eventually, compounds like hexachlorophene were developed. And they were pretty good. And some of the derivatives of hexachlorophene, you may have heard the name bisphenol, bisphenol A. They were added to plasticware. Okay, bottles, storage plasticware. And they were used to preserve food in those plastic bottles and containers until it was found that actually bisphenol A is toxic to humans, cumulatively toxic to humans. So now the statement BPA free, it's actually meaningful statement. As far as I know, all plastic, food grade plastic that's produced in the United States must be BPA free. Okay. One of the interesting sort of offshoots of using phenol as chemical for bacterial control was the introduction of phenol coefficient. Since phenol was one of the first antimicrobial chemicals, phenol coefficient was used to show how a particular chemical compares with phenol. So, say, phenol activity against Salmonella typhi is 1. Activity of Lysol against Salmonella typhi is 1.9. Not great, really. Activity of cetylpyridinium chloride is 228, so it's 228 times more efficient than phenol. Does that make sense? Phenol coefficient idea. Now, one chemical that I kind of want to mention, I just for some reason like it here. It's called p-cresol. It is a chemical. I don't know if you've heard about a substance that is called creosote. Some of you have heard about creosote. It can be obtained, derived, by heating up the wood without oxygen. Basically, you distill the sap and sap components out of the wood. It's thick, black mass, okay? Very viscous. I would say like honey, viscosity-wise. If you will walk along the old railroad track in a hot summer day, the railroad track that has not concrete but wooden ties, you will feel that very specific smell. Some people consider it unpleasant. I kind of like it. It's organic smell. That's creosote. Creosote was used to treat railroad ties to slow down the rotting process. And in fact, you can use creosote, and in some countries, I know that in rural parts of Russia, creosote is still used to treat skin wounds because it's antibacterial. I'm not talking about like deep cuts, like penetrating, terrible, bleeding wound, but if somebody has a lot of bruises, you can apply it and it will be pretty good, antibacterial. Okay. Now, couple of offshoots from the phenol story. One is triclosan. Remember antibacterial soaps, craze? I don't know if it was craze. Kind of. All soaps should be antibacterial. The main component of antibacterial soap was triclosan. A couple of years ago, FDA officially issued a statement in which it said that antibacterial soap does not have any superior efficiency compared to the regular soap. Because further studies after triclosan was introduced showed that first, triclosan is not that super antibacterial. And second, imagine how much triclosan went into sewage when people started to use antibacterial soap. And all that triclosan, not all of it, but a huge portion of it, ended up in the environment, turning environmental bacteria resistant to it. So even though it was marginally efficient, now it's not efficient at all. So FDA recommended to just stop adding it to the soap because there's no point. Now, there were claims that triclosan was toxic. Look, I can kill a person with sodium chloride. I can kill a person with table salt. Depends on the dose. Does that make sense? So in the doses that were present, in the concentrations that were present in the soap, in the concentrations that people could potentially be exposed to, unless they deliberately drink a bottle of antibacterial soap. Triclosan was not toxic to humans. It was not toxic to mice. It was benign. Okay? I mean, If you start feeding it, that's a different story. So, inefficiency, the main answer, why we don't use it. The one chemical that stemmed from the phenol story that is widely used now is chlorhexidine. The mechanism of action for chlorhexidine is the same as phenols, disrupts the membranes, denatures the proteins. It is not sporicidal, it's a disinfecting chemical. And its great advantage is that it's efficient and yet very safe. Those of you who work in healthcare settings, whether it's, I don't know, emergency room, operating room, long-term care facility, dental office, you know that chlorhexidine can be used in all those environments. In long-term care facilities, chlorhexidine is used for patient's bath. It's gentle, non-irritating, and very efficient in preventing the pressure wounds. In dental offices, chlorhexidine is used as the mouthwash. In surgery, chlorhexidine-based disinfectants and scrubs are used to either help surgeon to scrub before the operation or to prep a patient. There was actually a study comparing the efficiency of chlorhexidine and betadine. And it was a very interesting study because think about this. You know, the first hunch how to do the study is, well, we're going to take a patient, scrub the patient with iodine, and another patient with chlorhexidine, sample skin, look how much microbes are there. Well, is that your endpoint in this study? Patient doesn't care about the microbes on the skin. Patient cares about not having post-surgical infection. Does that make sense? So that study was performed in this specific fashion. They looked at the ratio of post-surgical infections and compared betadine, chlorhexidine, and they found no difference. So basically, they both are fine. Okay. Now this is kind of an interesting story, kind of an interesting switch. We're going from the ones that you're familiar with to the ones that you're definitely familiar with, but maybe not in that specific quality. The heavy metals. Okay? I want to write Slayer, but I'm not going to. Yeah, anthrax or something like that. So, we do use heavy metals in various antimicrobial applications. I'm going to talk about the mechanism first. General mechanism. They inhibit enzymes. For instance, copper inhibits enzymes of electron transport chain. What's pretty cool about heavy metals is that their effects are oligodynamic, meaning that they can control microbial growth in a very small, minute amount. We used to use even mercury for microbial control. When I was a kid, if you go get your teeth fixed, the cavity, they clean the cavity, and especially if you have to do the root canal, they will put amalgam to first prevent the infection and second kill the nerve. We don't use it anymore. Silver has been used as antibacterial chemical for thousands of years. Silverware isn't just because silver is so shiny. Actually, like pure silver is very soft and malleable, and the silverware, the bowls, like the kitchen utensils, they're super inconvenient. Like if you make a silver knife, it will bend when you cut something denser than, I don't know, fish. Okay, It's really malleable. But those silver bowls, silver flasks, bottles, jars, they prevented water from spoiling, wine from spoiling, because silver is a pretty potent antimicrobial activity. Some folks went a bit too far, and some folks decided to drink colloidal silver to treat, infections. That gave those people the condition known as arguria. You look like a Smurf. And then you die because silver is toxic to humans. You have gray skin with a gray to bluish and gray sclera. You look weird. Okay. Now, gold, same story. I mean, it's just more expensive. But same story, antibacterial. I'm going to skip copper for a second. Say a few words about zinc. Okay. So, you can find zinc in mouthwash. You can find zinc in certain ointments. The efficiency of zinc against the bacteria is somewhat debatable. There are some studies suggesting that zinc has inhibitory effects on the common cold virus. And, I mean, legitimate, good, well-done studies, but the number of those studies is limited. Okay? Now, one metal that got a lot of traction in the last few years in regards to its antibacterial properties is copper. Its antibacterial properties were first noted by, well, recorded at least, ancient Greeks. They found that, now that's going to sound kind of awkward, they found that shavings from the bronze swords, if those shavings were placed into the wound, prevented the wound infection. I guess nobody deliberately put sword shavings into the wound, somebody just accidentally got them there. And, with years they noticed that if you get these shavings on the wound surface, it prevents infection. So people used copper, as all you know, for storage vessels, for instance. And then copper antibacterial properties kind of were forgotten or ignored. But in the last maybe decade or two, they started to get back into the clinical practice. And in 2011-2012, a group of scientists and doctors, under the leadership of Dr. Michael Schmidt from Medical University of South Carolina, led a multi-center study in which they first identified the most bacterially contaminated locations in a typical hospital patient room. These locations included bed rails, ivy pole, computer keyboard, the armchair handles, stuff like that, And they sampled those locations and demonstrated sort of the average number of microorganisms. Now, that's total load. That's specifically Staphylococcus, that's MRSA. Gram negatives read, like E. coli, Losenterics, vancomycin-resistant Enterococcus. Now, the red line represents, this red line, represents safe levels, but let's acknowledge, it's not safe, it's acceptable. Safe is not to have any bacteria at all. So what they've done, they plated copper on all those surfaces. It's doable, it's a technical issue. And they demonstrated that on the surfaces where copper was plated, the number of recoverable bacteria decreased at least an order of magnitude. In some cases, for some microorganisms, they were undetectable, like MRSA or gram negatives, which is great. So, more hospitals now start to employ this approach, say, installing new doorknobs or new faucets. Now, you have to appreciate, though, that, bless you, if you have a hospital of the size of a Cleveland clinic and you want to replace doorknobs, that's like Lake County budget for a year, okay? Same goes for faucets. The price of copper plating bed rails on one hospital bed is $15,000 because you have to ship it out, disassemble it, plate it, assemble it back, ship it back. So now the idea is to incorporate plating into the manufacturing process, which will add marginally to the price of the bed. Does that make sense? So basically, like, if we need to replace the faucet, okay, let's replace it by the copper one. But if it works, it works. So gains traction. Okay, does that make sense? I found it a very cool story. And it's not just in one hospital. They did, I think, South Carolina, North Carolina, some hospitals, somewhere in Utah. So kind of all over the country, multi-center, and results are really good. Now, the last chemical methods, after which we're going to take a break, alkylating agents. So that fancy word, alkylating agents, means that these chemicals chemically modify DNA or protein. For instance, here, in this reaction, you can see that the guanine base is chemically modified into ethylguanine. It turns out that ethylguanine, instead of forming a pair with cytosine, will form a pair with thymine. So essentially, you have a replacement of a GC pair to eventually AT pair. These chemicals introduce mutations and instabilities into the DNA molecule, and they also denature or alter the structure of proteins. Okay? Forget about right. Okay? So, DNA is modified, proteins are modified, it all alters their function, and turns out that alkylating agents are extremely efficient. There are two big groups. One are aldehydes, other are modified alkanes. So aldehydes. Let's talk about formaldehyde a bit. Ever heard about formalin? 4% solution of formaldehyde in the water. Really good at preserving corpses. Okay. Actually, any biological specimens. Okay. Formaldehyde, pure formaldehyde, is a gas at the room temperature. It is used for decontamination of BSL-3 and BSL-4 facilities. I lived through decontamination of our BSL-3. So what happens? All operations are shut down. You take a tape and you seal everything. I mean, not every, but let's say you have a freezer with a lot of samples, important samples. You don't want the samples to be exposed to formaldehyde. You seal the freezer with a tape. Okay, seal everything that's important with a tape. And then everything that should be deconned, you open it up. And then you leave the facility for 2 weeks. They pump the whole place with formaldehyde. There's certain protocols, so they let formaldehyde to fill everything. Then they turn on the ventilation. It is sucked out. 2 weeks later, you walk in. A couple hours later, your head starts to hurt because it's not completely gone. Basically, what happens, you walk in and you wipe things down. So everything is safe. You can walk in like wearing a lab coat, okay? Because everything is deconned. If you need to fix something, you take it out. If you can fix it there, you fix it there. Like, you do maintenance. And then after formaldehyde was sufficiently removed, facility starts to operate again. Usually decontamination of this BSL facilities happens once a year. Glutaraldehyde and O-phthalaldehyde are liquids, and you need to know whether they're gas or liquid. Often used for treating, biological specimens. Ethylene and propylene oxides are both gases. Beta-propyl lactone is liquid. Beta-propyl lactone can be used for surface treating or biological samples treating. Ethylene and propylene oxide are extremely useful for sterilizing various plastic goods. Okay. Again, since it can be used like in the chamber, you can use this gases to sterilize research equipment. Does that make sense? So for chemical methods of control, you need to know the level of cleanliness. So for instance, alkylating agents are sterilizing and so on. You know, alcohol is disinfecting, blah, blah, blah. The mechanism. So for alkylating agents, chemical modification of proteins and nucleic acids. For, you know, chlorine oxidation. For alcohols, membrane disruption and protein denaturation. You know, this basic things. And that's basically it. Am I clear? So we're going to take a break now.